Hi Kiran, I am from ECB section. My topic is area aware cache update for trackers position post silicon validation. Introduction. The increasing complexity of modern processors has resulted in the evaluation of sophisticated post silicon validation features because the simulation techniques are inadequate for executing large test cases scenarios. During post silicon validation, sample chips are validated on the platforms where the execution is performed at the high speed, but elaborate mechanisms need to be put in the place to identify the cause of errors. Once faults are identified, recent research efforts in the area have investigated the both topics of bug localization and diagnosis, trace signal selections, and adaptation of test comparison techniques among several interesting designs for debug. Features used in industry today is dumping mechanism. The entire processor state consists of all caches and registers in various structures such as pipelines, register files, translation lookahead buffers, and recorder buffers. Capturing this state at regular intervals and analyzing sequences of such snapshots offline gives crucial hints on possible causes of errors. However, due to the large size of the last level caches, transferring each snapshot of chip is a time consuming process. We also require that during the dump phase, the process should not update the cache since it may lead to inconsistency. Therefore, the processor is stalled during the dumping phase. The duration of process stalls can be reduced by decreasing the amount of data that is required to be transferred off chip, such reduction in off chip transfer also limit the perturbation experienced by the test workloads due to the debug infrastructure. This significantly improves reproducibility of intermittent bugs. Another way to reduce the amount of data to be transferred off chip is by dumping only the cache lines that were updated after the previous snapshot. The straightforward method of storing the information on the lines that we are updated in the current dumping cycle is to maintain a bit vector where each bit represents a cache line and is set to 1 if the line is updated. This approach is also very efficient as the amount of processing required is minimal. However, its disadvantages is that the amount of space required could be unacceptably large for the large caches of modern processors. Since the bit vector size equals the number of cache lines, we attempt to store the information about updated cache lines in less space than the required by a bit vector representation and allow the designer to control the area overhead. The reduction in space utilized to capture the information on updated cache lines in our proposed structure may lead to a small increase in the number of lines transferred off chip. In case of distributed caches, updates to the all caches need to be tracked in order to obtain a consistent snapshot of the state of the processor. The naive way to achieve this is to duplicate the update tracker for every cache. However, this may result in significantly high area overheads. We aim to limit this area overhead by allowing multiple caches to share the update trackers. We propose a scheme under which the number of non-updated cache lines that are dumped off chip remains under acceptable limits. Even when the updated tracker is shared across multiple caches, the rest of these papers is structured as follows. Section: a pair of starting address and ending address, start address and ending address as interval. A set of k intervals is stored in the interval table. Unlike the previous method, this method does not partition the cache lines into fixed size sets. Instead, a continuous run of one in the bit of stored as an interval. The amount of storage required to store an interval is constant, irrespective of the length of the runs of the shades portion in a columns There are two adversarial situations to the interval based approach in practice. They are in bit vector, the actual number of runs ones can be very large, and the length of the runs can be smaller than the number of bits required to store their starting and ending address. To overcome the former issue, we merged some adjacent intervals to reduce the number of stored intervals to given a constraint. The effect of latter is sought to be overcome by the space saved when there are long runs. Since log 2 n bits are needed to address n cache line, storing a k intervals require 2k log 2 n bits, and it is essential that for interval table to save space over the bit vector. Therefore, the main challenge now is to capture the information of n runs. Merging adjacent intervals due to the upper bound on k will capture some non-adapted cache lines into the intervals, which leads to overheads. Thus, the intervals with the small runs of non-updated cache lines between them should be merged. However, determining the nearest intervals is non-trivial because of the online nature of the problem. Interval table needs to be maintained when the cache lines are being updated. Intervals that were far apart at same point in history can be become the nearest subsequent updates by the processor occur to the cache line between the two intervals. Conclusion: we propose two space sensitive techniques, bit vector and interval table, to keep track of the cache lines that are updated after the silicon validation. One major feature of the proposed DFT hardware called update tracker is that designer can tune them the tune them to match his area budget. Our proposed method is used to use a small fraction of the overall cache area with an average dumping overhead of 7.11.5% as compared with over 10% overhead of simple bit vector for a shared cache. We proposed a scheme to efficiently share the update tracker across multiple caches in order to further reduce the area overhead of storing the update information in distributed caches. We restrict the area overhead of the update trackers to less than 1% of the cache area in the case distributed caches to with an average dumping overhead of less than 2%. Thank you.